Thanks everybody for coming. This is a ongoing effort. We're going to talk about the scheduler, a very deep dive into it. I'm very excited about this because it's been, I think this like really started in earnest in like July of last year. Is that right, Matt? Okay. Yeah, so a lot of people are talking. This was a very collaborative effort, not just like between 3 different companies and many people, but also like engaging the full Dask community in order to figure out how to make all this go faster, not just for data frames, not just for arrays, not just for X-rays, not just for GPU folks, but for everybody. So with that, maybe James can kick it off after I share my screen.
You could share your screen, that'd be awesome.
Yeah.
Yeah, in the meantime, I'll introduce myself. Hi, everyone. I'm James. I work at Coiled and also am a Dask maintainer. And yeah, like Ben said, this is a large collaboration between lots of different engineers at different organizations. So specifically, NVIDIA, Coiled, and Capital One have been heavily involved in this effort. So I thought we would start this talk off at the end, actually. So Ben, next slide. Kind of the take-home message from this is that high performance computing isn't about doing one thing well, it's about doing nothing poorly. And hopefully we will drive home that point throughout the course of this talk. Also, Ben, not a huge deal. I do see the like URL stuff at the top. So I'm not sure if there's a way to somehow enhance, but it's also not a big deal if not. So anyways, yeah, maybe we can present. Look at that, great, thank you, Ben. Yeah, so just a brief overview for the talk today. So I'm gonna be here to provide a sort of motivating example and kind of tee up all the other speakers for the rest of the talk. We're then going to move on to kind of diving deep into different aspects of the work that has happened as part of this effort. So we're gonna talk about task graph construction and a lot of the sort of the overhauling of high-level graphs and proliferation of them as well. We'll then talk about serialization, profiling, Cythonizing the scheduler, and then we'll sort of hopefully put a nice bow on things at the end with some key takeaways and also future work. So next slide. I want to start with a quick example. So hopefully the text here is big enough for everyone. This is just something I did in IPython yesterday and took some screenshots. So we can imagine a simple example where we have some function f and it sleeps for a second to simulate some actual real work being done. And then it returns x plus 1, its input plus 1, just an increment function. We can then run this several times, in this case, 10 different times. And as we would expect, this thing takes about 10 seconds to run. Because each iteration of this for loop is independent of other iterations, it lends itself nice to parallelism. We can use Dask to do that. So we do that here. We instantiate a local cluster or and connect a client to it. And then we can take this f function and also run it 10 times, but actually simulate Dask to run it 10 times in parallel. And we see this, at least on my laptop, takes about 2 seconds. So we get a speed up factor of here about 5 seconds. This is great. Things are actually running in parallel. Dask is working. This is sort of a bread and butter situation for Dask. However, if we, next slide, yep, great, thanks, Ben. If we, instead of running f, which takes about a second, run a much faster function, g, which instead of sleeping for a second, sleeps for 0.0001 seconds and then returns x plus 1. We see this is actually just, if we run this in normal Python, this is blazing fast. We can run this thing 10 times, and instead of taking 10 seconds, it takes 1.61 milliseconds. So like, there's no need to really parallelize this. We can speed this up, or rather we can scale this up and like run this 1,000 different times instead of just 10, and we're still at like 100 milliseconds. If you wanted to run this actually in parallel with Dask, we do the exact same thing as before, but instead of running our function, our sort of functions that take a little longer, f, we run these really fast functions, g. We see that running with Dask actually takes more time. It takes something like 2 to 4x faster, or sorry, longer to run this with Dask. So what we're seeing here is that Dask isn't performing well in this scenario when the tasks are incredibly short. There's actually some overhead associated with using Dask that's starting to become the bottleneck in this scenario. Next slide. So we can sort of go back to the example when we're running this F function on Dask. And if you go to the Dask dashboard and look at the task stream, you'll see something that looks like this. It's basically just solid green all the way across. All of the threads and all of my workers are doing work pretty much constantly. We could zoom in a little bit into a portion of the task stream. Next slide. And what we'll see is there's like a tiny, and it's hard to see here, there's a tiny little sliver of white space in between these tasks being run. Yeah, thank you for highlighting, Ben. So it's a little hard to see, but it's there. And that little white spot is time when the thread pool executor on our workers, it's not actually doing any work. This is associated with the overhead of using Dask. If we then switch to what the task stream looked like when we were running our fast function G, here we see a lot more white space. We can then zoom in to a similar section in the task stream, and we see our tasks running, and they're really quick. And then there's a lot of empty space where our worker threads aren't actually doing anything before they run another task. So here, because the tasks are so short in duration, the overhead associated with using Dask is actually becoming significant. It's actually becoming a dominant factor in the performance here. I want to, in the next slide, actually zoom in a little bit and talk about the different types of overhead that are associated with using Dask. So we'll start with when you in your Python session, write some Dask code and hit compute, all the way to when those tasks actually execute on the workers. So we can see we have sort of the three parts of our Dask cluster here: the client where users live, then the scheduler, and the workers. So we have some example code here. The first thing that happens is you, the user, write some code, some Python code. You create a NumPy array, do some operations on it. You add one, you take transposes, you sum things together, and then at the end you call compute. And what's happening when you type, when you write this Python code is Dask is actually assembling a high-level graph under the hood. That's shown, that's sort of the first diagram that's shown there. Each little block in that diagram roughly corresponds to one of the operations that's happening in your Python code. So there's a little block there, there's a little layer there for creating a Dask array. There's another layer for adding one. There's a layer for creating a transpose. There's a layer for adding. There's a layer for summing, etc. This is sort of as the name indicates, kind of a high-level representation of the computation that you actually want to run. The next thing that Dask does is it takes this high-level representation and actually generates what's called a low-level graph, a low-level task graph. This takes this high-level representation and actually converts it and expands it into the actual functions that you want to run. So instead of having some high-level operation for transpose, it goes in and calls NumPy's transpose function on all the individual chunks in your Dask array. So this low-level graph generating it itself can be expensive. In particular, when you have large arrays with lots of chunks and lots of different operations, actually generating this graph can be one source of overhead. What Dask then does with this low-level graph is it actually goes through and optimizes it. There's an optimization pass where sort of any unnecessary branches from the graph can be totally culled or pruned from the graph. And also, we do another common optimization is task fusion. So you'll see, looking at the low-level graph here, on the very bottom, there's like a string of tasks, like a little kind of small tower of tasks that get all fused into a single task. So this will, in general, reduce the complexity of the low-level graph and sort of generally make it smaller. But even the optimized graph can be really large and complex. The next step is to take this optimized graph, actually serialize it, and send it to the scheduler. So for serializing this graph, we take this, Rick will get into the details of what the graph structure actually is, but we take some Python dictionary and we convert it to a string of bytes. We then take that string of bytes, send it over the wire from the client to the scheduler. And then on the scheduler, we undo that serialization. We deserialize. We take the string of bytes and actually reconstitute the optimized graph on the scheduler side. And each step there can be expensive. The serialization step, the communication step, the deserialization step. The scheduler then takes this optimized low-level graph and updates its own internal state in accordance with sort of the tasks you have asked it to run. So at the end of the day, the scheduler ends up updating a bunch of like dictionaries. That's sort of the internal state it keeps track of, a bunch of Python dictionaries. That updating state can also be expensive. Once that's happened, and the scheduler is now sort of aware of all the tasks and knows all the priorities and dependencies and things like that of the tasks you'd like to run, the scheduler then starts to farm out those tasks to workers. So the scheduler will send tasks off to all the workers in your cluster, and the workers will start doing their work. All the while, the scheduler and workers are constantly communicating back and forth with one another. So there's this concurrent conversation that's happening between the scheduler and all the workers. You know, the scheduler is sending tasks to the workers. The workers are letting the scheduler know whenever it's finished certain tasks. The scheduler is then sending more tasks to the workers for them to compute. The schedulers are also just kind of periodically sending heartbeats back to the scheduler. So the workers are just constantly saying, hey, scheduler, don't worry, I'm still alive. Here's some information about me. I have this many tasks I'm executing, this many tasks in memory, just sort of constantly communicating with one another. And that introduces some burden on the scheduler, having all these conversations with all these workers at the same time. For many clusters, for like small number of workers, this is not a big deal. However, next slide, when you have lots of workers in your cluster, this constant communication between the scheduler and the workers can become a burden on the scheduler and on the performance of your cluster. So that's sort of a high-level overview of the different types of, what am I trying to say? The different types of, or I guess really what happens under the hood and the different types of overhead which just running Dask requires. So for the rest of the talk, we're going to dive into more detail into these different steps in this diagram, as well as talk about some of the work we've been doing to improve performance at each of these steps. And so with that, I will hand it off to Rick.
Great, thanks, James. All right, so yeah, James just did an excellent job of motivating the overall problem. And he showed an illustration that really made it clear that, you know, as we want to scale out our problems in Dask, there are bottlenecks, especially on the scheduler, and you know, as you increase the number of workers. But there's also this clear bottleneck on the client side. The client needs to actually construct this graph to begin with, needs to run optimizations, then it needs to ship it over to the scheduler. And this can be a non-trivial amount of time. So I'm going to go into some details of what we need to know to understand what the graph is that we're constructing and how we're trying to improve performance here. So next slide. First of all, it's useful to know what is a task graph in Dask, or as James referred to as a low-level graph, and we often do. It's really just a dictionary. It's a Python dictionary where you're showing some, you're specifying some dependencies between keys and tasks. So up on the upper right, you see this is an example of some part of a task graph for the example on the bottom left. So the example on the bottom left is we're just going to take a pandas series. We're going to convert it to a Dask collection, and then we're going to get the sum. So this is pretty simple. What it's going to do is create a big long task graph that's going to have keys for each of the individual, each of the partitions. Here it's actually got a literal value for these keys. And then it's going to have all of the keys and dependencies for the different tasks that are required for your tree aggregation to calculate the sum. And so on the bottom right, we'll show kind of like a high level, like a graphical visualization of what this task graph looks like. Just a warning though, this is actually shown after optimization to make it a little bit easier to see. So this, you know, each of these nodes actually has multiple tasks fused together. Next slide. And so there's a difference between the low-level graph and the high-level graph. The low-level graph, the materialized task graph shown on the bottom left again, you know, there's a dictionary of keys and tasks. Tasks are just tuples where the first element is a callable In this case, it's the an apply, which is just a convenience function in Dask. But we also, when we are using most collection APIs, are constructing a high-level graph under the hood. So a high-level graph, in contrast to a full materialized dictionary, is just going to have a list of what we call layers. So on the bottom right, you'll see there are 2 layers in this particular operation. There's from pandas, so it's our IO layer. And then there is going to be our tree aggregation to calculate the sum. And so I showed up on the upper left that, some of these tasks got fused together, so it's hard to tell, but the first 2 tasks would have originally be from pandas, and then the rest would be this high-level graph layer to do the tree aggregation. All right, next slide. And so some important things to consider about a high-level graph. The thing that makes it so powerful is it can be very quick to, or very fast to construct a high-level graph. You maybe need very little information to say, hey, there are this many partitions. We're going to apply this function to every single one of those partitions. We don't have to materialize a full graph, and so it can be very fast. Also, something to consider is before all this work was performed, there were no specifications on what exactly a layer was. It just had to sort of inherit from a mapping, and so it was pretty much just behaving like an underlying dictionary. Each layer, it was just a layer. So what we really had was effectively a dictionary of dictionaries. All right, next slide. And so this is just going back to a slide that that James already showed, but it's a little bit different. This is showing an example that we are sort of focused on, perhaps in on the client side as being an issue. So if you create a time series and you shuffle it and you take the head, if this is a really large time series, you might end up waiting a long time on the client just to construct and to optimize the graph and everything. Because what you're doing is you're first constructing a high-level graph, and then when you want to send it to the scheduler, you're maybe optimizing the high-level graph, then converting it to a low-level graph, and then you're going to optimize a low-level graph, and then you're going to send that over to the scheduler. And all of these steps can take a non-trivial amount of time. All right, next slide. And so this is just reiterating everything we've just talked about so far. We care a lot about all the things going on the scheduler right now, on the client right now. So this is the ways that the cluster works together. First, you are creating the task graph on the client. You got to construct it, optimize it, serialize it, upload it to the scheduler. The scheduler is going to do, it's going to download it from the client, do some serialization. And so we have a lot of time in between, the API calls, which are constructing the graph, and then the actual execution of the graph on the scheduler. All right, next slide. And so this is kind of giving you an idea of what do those times add up to, before it actually gets to the scheduler and executed. This is just showing another example where I would do time series, shuffle, and then head, showing almost exactly the command I'm using, but just for reference, because there's a bunch of junk in time series to get this exactly right. I got 17,544 partitions for this particular case. You'll see just calling, just creation of the high-level graph, really what it is 4 seconds here. And then you call optimize, and that's taking another 1.3 seconds. So what, we'll talk a little bit what Dask optimize does, I think a little bit later, but it's first running some high-level graph optimizations, and then doing these low-level, culling and fuse. And then we need to serialize it. So this is giving a rough estimate of about how much time you would expect it to take to serialize that graph if you're using something like Pickle, about 700 milliseconds, and then a rough estimate of how much it would take to send it over the wire. If you're assuming about 100 megabytes per second, this could take another half a second. So next slide. And so altogether, if we're just talking about all this client-side time, it really does add up to maybe 6 seconds with that head. Notice I was just at the end of that command, I was taking the head, so I only care about the first partition in the end. But if I wanted to get the whole data frame, just on the client side, no work has actually happened on the scheduler. Nothing has been executed. It would take closer to 15 seconds. All right, next slide. And so what is our solution to this on the client side? In this larger effort, we want to attack this whole end-to-end process. We want to make the client side faster. We want to make the scheduler faster. Well, the idea is, let's not, let's make high-level graphs much more effective. And let's not materialize the low-level graph on the client. Let's send a really effective high-level graph over to the scheduler, and let's allow the scheduler to materialize that, quickly and start scheduling right away. And so this is go back to the same example. This is how it was, how things were flowing before. Next slide. And this is the plan moving forward, is that for that same exact example, we will construct the high-level graph. We will optimize that high-level graph and make those optimizations, better than they were before. Then we'll send that optimized high-level graph to the scheduler. The scheduler should be able to materialize this faster than, say, it would have taken to send it over the wire and have the scheduler process it from there. And so everything else looks, pretty similar, but I'm going to let, the scheduler work. Others will talk about what's going on in the scheduler. So this all sounds great. Let's do this maybe, but there are some requirements. There are things missing. Back when we started this work, there were some big things missing. And so let's talk about what those were. So there are a few requirements for sending the HLGs to the scheduler. First of all, we need optimizations that are replacing the low-level optimizations that we have been relying on. The most important of these are calling and fusion. For example, for the head example, right? In the end, we'd only need the first partition to get the head of a data frame. If we have 1,000 partitions in our data frame, we don't want to send that whole graph over to the scheduler because it can be much, much larger than what we actually need. And so we want to achieve that. Also, task fusion right now at the low level. Dask will do a good job of fusing together tasks that are, have the partition-wise operations, and there's no reason for them to be two separate tasks. We want to achieve that as well, especially when it comes to I/O, where it can be particularly important that an I/O task is fused with a follow-on task that's just doing something simple like a get item or adding one. We also need to be able to, I'm sorry, I'll just say a couple more things. We also need to be able to serialize and deserialize the high-level graph. Starting out, the scheduler was not able to, so we were not able to send the graph from the client to the scheduler. The machine learning just wasn't there. And also, we need to make sure that the scheduler can materialize this high-level graph once it gets to the scheduler. All right, now I'm ready for the next slide. All right, so general prerequisite, so a lot of this work was attacked by Mads early on. He did an excellent job. Props to him. He's going to talk about serialization and deserialization. And one of the first things that we decided that we needed, also a big, this plan came a lot from Matt Rocklin, was something needs to be consistent in the specification of a high-level graph. We can't just have random high-level graph layers that are all doing different things. So we decided to come up with a unified layer class so that all layers in a high-level graph have to inherit from this high-level graph layer. So that this high-level graph layer can make sure that we're taking care of serialization, deserialization, and calling. All right, next. And then calling, yeah, a little bit more detail about that is that calling actually becomes pretty simple once you have come up with this standardization of everything needs to be a layer, because you just require that there is a layer.call method. And all you need to do is loop through the different layers in your graph and make sure you're starting with the end keys that you need that you're expecting for a computation. And then you just are passing information to each layer. The cool thing about calling a high-level graph is you do not need to actually materialize a high-level graph to do the calling. It might just be that there's logic in the layer itself that just knows, oh, if I only need to output partition 0, I'm only going to construct a graph for partition 0 when I need to materialize one. All right, next slide. And here's an example of that in practice. So here, the same example, time series, set index, and then you take the head. Here at the top, we have the original high-level graph. And what I'm pointing out is halfway through there, we have what's called a shuffle layer. Shuffle layer was one of the early layers that we made sure to do a good job with calling, because it's quite important to do calling on a shuffle graph, because this is just 2 partitions. If you go and say, okay, well, I want to have many, many partitions, the shuffle can explode in size. And so we want to make sure that we are calling this for sure. And so here, the second layer down, you'll see task graph without high-level graph calling. Of course, I'm only using 2 partitions, so it doesn't look huge, but it can get really huge. And then task graph with high-level graph calling, you'll see that we have automatically gotten rid of these extra tasks here that we didn't need, and it became a much simpler tree. The cool thing to keep in mind, I'm going to reiterate this again, we didn't actually need to materialize this to get the calling. This graph down on the bottom is what is materialized on the scheduler automatically. We didn't have to construct a graph and then call after the fact, which is exactly what we're looking for. Okay, next slide. And so there's another missing optimization that we needed in the high-level graphs, and that was fusion. So there's still ongoing work in this space of like, well, how do we achieve all of the fusion that the low level graph optimization path was doing? But a very important component of that, like I said before, was we want to fuse IO tasks with follow up, partition-wise tasks. And the nice thing is, it turns out that blockwise, a layer that already existed in the beginning of this work, already does this. There's already, in Dask data frame and in Dask array, a path where we check, oh, do we have blockwise layers? If we do, let's try to fuse them all together if possible. And so we said, okay, well, we can take care of IO fusion by changing all IO operations to be blockwise operations. And so this is exactly what we spent a lot of time doing. You might have noticed if you've been following any development in Dask data frame or just Dask in general over the past 6 months, there have been some churn and some back and forth putting this in and then taking it back out. But I think we're getting to be in a good state now. Next slide. And so this is just an example of what it looks like in practice right now in the main branch, right? So we have something called a data frame IO layer. So if we're doing something like read Parquet, and then we do a get item selection, and then we add one, for example, we'll have something nice here. We'll actually have a high level graph that has a data frame IO layer, then a blockwise layer, then a blockwise layer. But data frame IO layer actually inherits from blockwise. So when we call the high level graph fuse without even materializing the graph, this all gets fused down into a single blockwise add layer. So that when you materialize the full task graph, you have a very much simpler task graph than you did before. And this is exactly what we're looking for. Okay, next slide. And so this is just kind of summarizing for a real world example. If you kind of wanted to see, because these were all toy examples before, if you want to compare like before we started all this work to, very recently, what the differences looks like on the client side, the same example running before and after, you'll see this big gap in the beginning where the client is really like right here, nothing's going on, but nothing is happening because this is all graph optimization stuff, all client side overhead. And so this is a case where we're saying, okay, we're really starting to see gains here on the client side. This is great. But the problem is now we need to improve this performance of the scheduler, right? Because we've just moved graph materialization and provided even more overhead for the scheduler. So for the rest of the talk, we're going to talk about the scheduler. That's it for me, I think. Oh, I should have said after serialization, but serialization is a big important part. So now we're on to Mads. Mads is going to talk a lot about some of the problems we ran into just being able to ship the high level graph over to the scheduler.
Yes, thanks. Yeah, my name is Mads, and I will be talking a bit about the serialization, both generally how that works in Dask distributed, but also how it relates to high level graphs and how we did the serialization. Next slide. Yeah. So first off, why not just use Pickle or Cloud Pickle? I mean, if you're going to serialize, why not just every time you send from one component to another, say from the client to the scheduler or to the scheduler to the workers, why not just pickle all the messages you're sending and unpickle at the receiving end, right? That should be the most straightforward approach. And the main reason why that's not doable is security. The model in Dask distributed is that we want this isolation of task execution. So it's only the workers that run tasks, right? So the client will submit tasks, submit functions to be run to the scheduler, but the scheduler will always delegate those tasks to workers to do the actual execution. And so you can have a setup where you can, in the configuration of your cluster, whatever, you can set up saying that the workers is isolated in some kind of a sandbox mode, and then the scheduler can be more free to where it's located. And the problem is that unpickle is not safe. It will allow running in any code. So basically, a hacker could just send a message to the scheduler with some arbitrary code to be executed. And so in order to avoid that, we cannot just use Pickle for everything, at least. Next slide. Another reason is performance. In Dask distributed supports many protocols. So in the most common case is the TCP protocol, and in that case, it might make sense to use Pickle and something like that, because you are at the end you are basically serializing to some byte strings, and you send those off to the wire to either from the client to do scheduler or the scheduler to do worker. But imagine if you're using UCX, which is another protocol you can use that supports direct GPU communication, which means that if you are communicating a CUDA array or something like that, it will be copied directly from one GPU to another via NVLink or something other like that. And so it doesn't have to necessarily have to go through the CPU and the main memory. And so if you are using Pickle or something like that, you would kind of force that extra communication path, and there's not really any need to do that. Finally, you have some like in-pros in-pros protocol where it doesn't need any serialization at all. So clearly, we have to do some other than just Pickle everything. Finally, we also want to minimize the number of serialization and deserialization cycles. So you can imagine that a component might not, for instance, the scheduler might not have to deserialize everything. Say you're sending a NumPy array and many gigabytes of array. It might not be necessary for the scheduler to understand exactly what's going on, what's the value of the NumPy array, but just rather that it's a NumPy array of this size or whatever. And so it doesn't really make sense to serialize at the client, deserialize it at the scheduler, and then serialize it again just to send it to a worker. So performance wise, we want to do something other than just Pickle everything. Next slide. So DAS Distributed uses message pack for everything. So instead of using Pickle, it uses message pack to do all serializations between workers, clients, and the scheduler. At least if you're running TCP and the UCX. Because in the in-process proxy, we don't need to do any serialization at all. Anyway, so message pack is inspired by the JSON format. It's fairly fast, and important feature is it's secure. So it will not run arbitrary code. It only has some fixed types it supports. So it has this basic Python types like float point, integers and strings, bytes, stuff like that. But it doesn't support NumPy arrays or functions or data frames or anything like that. It's very basic. The basic primitives in Python it's the only one it supports. And so the idea is that message pack will begin serialize when you send something from, say, the client to the scheduler. Message pack will serialize this data, and if it encounters objects that it doesn't support, it will be that object will be handled out of band. And so the idea is that Dask has a bunch of serializers that can handle potentially everything. And you have some families like the Dask family or CUDA family and others, and you can even register new serializers, and they can be specialized based on the exact data you're sending. So you can specialize for NumPy arrays or for Pandas data frames or for QPy CUDA arrays and stuff like that. And they are allowed to be unsafe. So that's the thing. They can just do whatever they want, and deserializing using these serializers is fine if that's unsafe, right? And they would, most of them, and most often you would probably have Pickle at the end. So functions and general stuff, you just use Pickle if there's not any specialized serializers. But they can be unsafe, and that also means that the scheduler will cannot deserialize them. So everything that the message pack cannot serialize, and so will be handled by these out-of-band serialization, cannot be deserialized at the scheduler. So they will just be passed through. So imagine you have a task that's serialized. It's a function. It's serialized. That will just be passed through to the workers as is. And then it's up to the worker to deserialize them. Next slide. And that's some challenges because how are the schedulers supposed to handle? I mean, so you're sending tasks that consist of functions. They are serialized by this out-of-band serialization. Now they arrive at the scheduler, but since they are specialized and just a blob of bytes, there is no dependency information in there. The scheduler cannot modify task, can modify keys, because that's just a blob of bytes, and it does have no way to know what that blob means, and it cannot edit that blob, right? Because it is not allowed to deserialize that blob. So this is a major challenge, and particularly into this high-level graph issue. Next. So recall for just from before. It used to be that the client would do all the work, right? So it have the high-level graph, it converts to a low-level graph, materialize the graph. It could do optimizations on this graph, and at the end, it will just send the graph to the scheduler. I think there's an echo now. For me. Okay.
Adele, I think you're should be.
Okay, I'm just saying. Fair enough. Anyway, so the optimized graph then sent to the scheduler, and that's and the scheduler can then do the internal state machine. Next slide. Now, with our works that we're talking about today, we have changed this so now the client is just basically handing over the high-level graph to the scheduler, and so we need to serialize the high-level graph and have the scheduler do all the work, right? So the scheduler will do the materialization of the high-level graph, and the scheduler could generate the low-level graph. And if we have other optimizations that was already done on the high-level graph, it should also be the scheduler doing that. But how can the scheduler do that if tasks are serialized and you don't have any dependency information, and you cannot modify keys and tasks? Next. So basically, our approach, we realized that we need to do some pre-processing on the client, and we cannot simply just send a high-level graph to the scheduler. We need to process it both to make it serializable, but also there are some stuff here that we need to do at the client where we can do basically anything and not restricted by this security issue. So first off, all layers in the high-level graph, we'll need all the keys in the high-level graph in order to calculate the dependencies. This is a very important issue. So remember that each layer in the high-level graph might not be materialized. Most of them are hopefully not. If you have blockwise or shuffle layers and all these layers, they are represented as layers in the high-level graph. But we still need all the keys they will generate in order to calculate dependencies. And we need to calculate the dependencies on the client before sending it to the scheduler, because the scheduler cannot calculate dependencies because stuff has been serialized. And so and dependencies must be calculated before serializing the task, right? So before we kind of serialize the task and we remove all information of that task, we don't know then. At that point, we don't know what the task will access, what keys are input, what keys are producing. We don't know anything about that. So we need to serialize, we need to compute the dependencies before doing the serialization of task. Also, before serializing, we need to unpack remote data. So on the client, if all the handles you have as part of your calculations, so that would be all the futures on the client, we need to unpack those futures and convert them to keys that match the internal state of the scheduler. And again, we need to do that at the client. And finally, generally, it is like a task graph. A key in a task graph is just something that are hashable, right? So typical tuple or something like that. But on the scheduler, it has to be a string. And so again, we need to stringify it before we can do the serialization, because we need the keys that are embedded in the tasks that are serialized. We need those keys to be stringified at this point before they are serialized. So just the whole point here is we need to do a lot of stuff at the client. Next. So we came up with that approach where we didn't have to materialize and generate the low-level graph in all cases before sending it to the scheduler. So the idea is that we have on the client, we have an interface for packing a layer. So the code just below the client, as you see in the slides, that defines this Dask distributed pack method. And that's basically going to be the responsibility of serializing the layer and must produce something that is message pack serializable. But that's the only requirement. So if you implement your own layer, you need to provide this pack function, and it should produce something that are message pack serializable. And it gets input, it gets all the high-level graph keys, so you can calculate dependencies inside this method, and also known key dependencies. So we don't have to recalculate dependency keys that we already calculated. It turns out that calculating keys is also a fairly big overhead, and doing it over and over again can be quite expensive. So you get all the keys that has already, the dependencies that are already be calculated. Now, if you, maybe I should say on the other end, we then have the scheduler will call the Dask distributed unpack method in order to get a real low-level layer, or get the low layer back. And it, as an input, it gets the pack layer. So that's the state, which is the stuff that was packed and are message pack serializable. And then it gets a dictionary. That's basically the graph from all the preceding layers. So all the layers that has already been unpacked, it gets that, and then it gets all its dependencies. Because remember, the scheduler cannot calculate dependencies. And then what it will return, the unpack function returns then a dictionary of basically the low-level graph and its dependencies, and those just match perfectly to the rest of the scheduler implementation. So that will just be passed down the scheduler and given as the new updated graph, and that will be merged into the overall state of the scheduler. Now, if we have this fallback or the default pack method that we're going to use if there's no any specialized layer definitions, and that one will unfortunately be very expensive and will materialize the low-level graph at the client, and then it will unpack remote objects, the Dask futures, and it'll do stringification, and it will pack annotations, and finally serialize tasks that are not message pack serializable. So this will just do most of the work, and so if there is not any specialized pack function, we will have to do all this work, and basically losing most of the work of the performance improvement that we usually getting having the high-level graph directly to the scheduler. But of course, the idea is that each layer, high-level graph layer, can specialize around something. So, for instance, you have a blockwise layer, we have a shuffle layer, and blockwise dependency layer, and all of those implement their own pack function. And then they use the domain knowledge. So, for instance, blockwise say, okay, I'm generating the graph based on these blocks of data, right? And they will generate basically running a function on each block. So it will pickle the function and say this blob of task is just pickled at the client, but all the generation of the graph, we don't have to do that, because that information is just passed to the scheduler, and then it's the unpack of blockwise that will materialize the low-level graph, put in the function that's going to run for each block, and then it's finished. And then you have to be careful about making sure that it also stringify the keys and stuff like that. And so for each specialized pack method, you have the corresponding specialized unpack method. Yeah, and I think that's the last one. Yeah, so that was serialization.
Cool. Thanks, Mads. I'm Gabe from Coiled, and I'm going to talk about some of our profiling efforts. So we've heard a lot about these like pretty intricate ways that we are looking at improving the performance of scheduling. But as with any effort to optimize anything, it's essential that you profile and measure what you're actually doing, because one, you want to make sure that the thing you're optimizing is the thing that actually costs you time. And two, as you're making these improvements, you want to make sure that things are actually getting better. So in profiling any distributed sim is very difficult. Luckily, in this case, we're simplifying that problem because we're not actually looking at trying to profile the entire Dask system at once. We're focused on this one component of the scheduler. So we're trying to profile kind of this one Python program. But even that proves to be a little difficult because in part of Python and the fact that there are a lot of different ways to skin a snake and to profile Python code. So we can see a number of different tools that we have used over the course of time to try to profile performance of the scheduler. We've used Dask's built-in profiler, we've used Python's built-in profiler, we've used Perf, we've used NVIDIA Nsight, VizTracer, PySpy. There's probably some others that aren't on this list. And they're all kind of like wrong in different ways, and you just have to know how they're wrong and like be able to think about all of them together. So for this, I'm going to go over a few that we have worked with specifically, Dask's, cProfile, and PySpy. And so they all have different trade-offs. For example, like Dask, next slide, Ben. Dask profiler thing, it's built into Dask. It's distributed, that we didn't actually need that part. It's inaccurate in some ways. There's cProfile, which is built into Python. It's built into Python, so that's easy. It's inaccurate in different ways. And then last, I'm going to talk about PySpy, which is inaccurate and yet a kind of another way from all the others. But it has some good compromises between kind of like having too much information and being too granular and still being able to understand it at a high level. And so all this profiling work has been sort of going on in parallel with a lot of these different optimizations. And a number of different people have been working on it, but I'm just sort of taking their work to talk about it here. So a lot of this started with the Dask statistical profiler, and this probably looks familiar to some of you because this is built into Dask. So if you've ever clicked on like the profile tab on the scheduler dashboard, you've seen this. So this was a great place to start in trying to understand what was going on with the scheduler when it was running big workloads. Since all you really have to do is capture a Dask performance report, which is already something that exists. It basically like saves the state of the Dask dashboard to a static HTML file, which is great because you can share it with other people and talk about what's going on. Very low effort to look at this. The way that this profiler works is it's a statistical profiler. And a statistical profiler means that at some set time interval, say like 10 times per second, the tool looks in Python using some like Python introspection methods to see what are all the functions, what's like the current stack frame, or what are all the frames that are currently running, what are all the Python functions that are currently running, and it aggregates that over time. So what you end up with is a picture of like which functions were we most commonly in when I checked. And because of statistics, that gives you a pretty good overview of like, where are you spending most of your time? It does mean that you can theoretically miss really, really short running functions, but hopefully if they're really, really fast, then you don't care about them as much. It's not always true. But that's sort of one of the downsides of using the statistical profiler method. What we found from looking at these profiles, the main thing that stood out was that there was a lot of time spent in reads doing IO or doing IO and deserialization and other. And with some more investigation, we kind of realized that this wasn't as simple as saying, oh, IO is slow, or like, oh, reads are slow. There are actually maybe some much more nuanced things going on in how Python works, particularly around the global interpreter lock, where potentially it's not that the read itself is actually slow, but that when we read from a socket, we release the GIL, and then in order to return from the read function, we need to get the GIL back, and someone else might have the GIL. So we might actually be waiting to get the GIL back, but we're done reading, and we're not capturing that sort of like much lower level nuance in these high level statistical profiles. That theory is unconfirmed. I think we're actually starting to realize it may not be as much the case as we originally thought, but kind of the takeaway from looking at these profiles was that we needed more tools to try to look at this problem, because one, there were lower level things going on potentially, and two, we lose some information through this aggregation. Like you can see this flame graph, it tells you like this thing took a while and it called some other things, but you don't really get the full picture of like, why did it call this? Like, were there lots of little calls or one big call? What's the distribution like? So then we turned to some more tools. So we tried using cProfile and visualizing the results with GraphViz. cProfile is the built-in Python profiler. It's unlike Dask's, it's a deterministic tracing profiler. So instead of like sampling every 10th of a second, it just tracks every time a Python function is called, it tracks how long it takes recursively for all the things that it calls. So it captures everything that happens, no matter how small. This is good on one hand, because it means you don't miss anything. On the other hand, it can also lead to some bias, and it generally means it has a little bit higher overhead in runtime. But the great thing is we have way more information. The problem is we have way more information. So when you run this over like a long computation that takes 5 or 10 minutes, you get tons of information, kind of too much to deal with by just looking at it. A common thing to do is to just look at, okay, what functions out of these took the most time? What did I spend the most time in? That's kind of what you're looking for. The issue here is that you, again, sort of lose the context on how do these functions relate to each other? Like, why is this happening? And so we use the gprof to dot utility script to convert the cProfile output into a graph, which lets us visualize like a call tree of how all these functions relate to each other, and it colors them by runtime. So this is a result of profiling a shuffle workload on the scheduler from end to end. And what you can see is that like the red stuff, it's colored by total time of the entire operation. So the stuff at the very top that's all red, those are functions like asyncio.runForever. Run forever should take 100% of the runtime. That's how it's meant to be. That's not an issue. It's the things that happen within that we're interested in. So about half of the time is spent in select epoll, which is like waiting for something to happen on a socket. This is great. We would love to be spending 100% of time in select, because that means that the scheduler is so fast that whenever it has something to do, it gets it done immediately, and then it just gets to like kick back and relax and wait for someone to bother it again. We're interested in the other time where it's actually doing something. And what we found from looking at these graphs was that kind of a lot of that time was spent in task transitions. And so if we zoom in here, you can kind of see how like there's the very dark blue and the slightly less dark blue and the like greenish blue. And that's the weighting by total time. So we're going to focus on that box that's like the little box that's in the middle of the big white box. So that is the transition function on the scheduler. And we found that the bulk of the time was spent in here, and in a little bit, we'll zoom in on this so you can hopefully read the text. But it came out to be about like 15% of total runtime of the scheduler. So this transition is sort of like kind of the heart of the scheduling logic. It's what happens whenever something changes in the task state, like a worker completes a task, or the scheduler learns about a new task from a client, or a task starts running that wasn't running before. All of that goes into the transition function, which then decides like, okay, based on this change in state, what should I do next? Or like, what else does this mean I need to do now? So this is like a very important function in the scheduler. And from looking into these profiles, we're able to find that there were some utility functions that were taking longer than we wanted to. Another interesting finding was that there was communication happening at various times. So like IO, sending messages back and forth. And what we found was that doing like a bunch of small read or write steps is less efficient than trying to batch them all together. So we were able to, John was able to refactor transitions to batch more of this communication together, which did have a nice performance improvement. And next slide, we'll just see this zoomed in a little bit more. It's probably still kind of hard to read, but if you put your face close to the screen, you can see that like, yeah, 15% of the time in transition, and then like a bunch of other stuff we call out to, which is all relatively fast. So it's this sort of annoying problem where like, there's no one thing which we need to make faster. It's like a bunch of kind of spread out a bunch across a bunch of pieces. So the next thing we went to with profiling, like this was helpful and this got us some gains, but there was another question here, which is all of the stuff we've looked at before. This was all running generally on a single giant machine, like a machine with a couple dozen cores and hundreds of gigabytes of RAM. It was running a big workload, but like all just on a local cluster on this big machine. We wanted to take a look at what things look like in a more kind of real world scenario where you have a distributed cluster. The workers are all separate machines. There's network in between them with real latency. And we also kind of wanted to get more of a picture of like a more granular picture of what was going on. So we tried using PySpy, which is a statistical profiler again. So it samples 100 times a second. That's the sampling rate we went with because it's the default. It's written in Rust. It has a pretty cool model where like it's actually totally independent from the Python process. And it uses some Linux tricks to like spy on the Python process's memory and go traverse through the data structures of the Python interpreter and interpret them to understand what Python is doing. This is kind of cool because it's completely separate from the like Python code that's actually running, which is sort of nice for some like other garbage collection-y reasons. It has pretty low overhead for the amount of information it's able to capture. And in my opinion, the best thing is that it captures the sequence or like the timeline of what's happening, as opposed to this aggregation. So you're actually able to see like at any given moment in time, what was my program running? And that combined with SpeedScope, which is this WebGL visualization tool, it gives us a nice way of looking at what's going on, both like at a very granular level and at a big picture level. So we can see here an example. Oh yeah, this is what we ran. So we ran this on a 100 worker cluster where each worker had like one CPU with a separate EC2 instance in Amazon. We use this PySpy on Scheduler Context Manager. If anyone is interested, this is like a thing you can, it's on my GitHub, you can install it if you want. Could be handy for someone else who wants to profile what's going on with the scheduler. But we make a time series like we've been doing in this presentation, a synthetic data set, and then we shuffle it. Shuffle is a good benchmark here because it requires tons of communication between tasks. Really the limiting factor is like how fast the scheduler can tell workers new things to do. And this is what the results look like. So this is the timeline view like I was talking about. So on the left, the first block, the idle block, this is where we're waiting for the client to tell the scheduler to do something. The thing to notice there is like kind of the bottom layer of things is like brownish. If this was in SpeedScope, we'd hover over it and we see that that's the epoll select function where we're waiting on IO. So already this is sweet. It tells us like, when are we doing different things in the workload? We can see that idle time's happening at the beginning. And then there's that kind of like block of wide calls. That's where we're lowering the high level graph into a low level graph. If you remember, like Rick showed, it takes a non-trivial amount of time to turn a high level graph into a low level graph. It's unsurprising that when we move that work from the client to the scheduler, still takes some time. Once that has been done, then we compute. And this is kind of interesting because like there's no one thing in this compute section that stands out. You're not like looking at it and it's like, oh, there's some function which seems like 5 seconds and like it happens a few times. Let's work on that. It looks like lots and lots of calls to functions which all go pretty fast. The other thing to notice is that there's no brown in there. There's no select. So that indicates that we are scheduler bound. we're not like, the scheduler doesn't have any opportunity to like finish what it's doing and wait for something else to do. It's like always trying to catch up with like the latest messages. So that's helpful for us to know. The cool thing, next slide. Yeah, we're scheduled bound. Next again. Yeah, so the cool thing about Speedscope is it has this really nice left heavy view, which is this kind of a typical flame graph view where it aggregates, you know, all those little slivers, everything with the same name gets put together into a bar, and then it puts the longest ones on the left. So this is sort of a nice visual breakdown of where are we spending the most time, and it lets you see like what we're calling in those things that are taking the most time. So as before, we can see that these transition functions in handle task finished are still taking a substantial amount of time, the thing furthest to the left, but there's also a bunch of other stuff that we're doing. So as we had thought initially, reads are taking up quite a bit of time. Interestingly, a lot more than writes. We also see the high level graph to low level graph lowering, and this is relatively new, so there's probably some room to optimize that a bit and make it run faster. It also tells us that attacking that could have a meaningful impact on performance because it does take up like a good percentage of the total runtime. And then there's also some Tornado, which is the like IO framework we use. There's some Tornado IO overhead, and kind of one interesting thing to look at visually in this view is that if you look at both like the COM read section and the Tornado IO section, there's very much like a kind of tapering in of the profile. It's not like a vertical bar where like some high level function at the top calls a bunch of other things and it ends in like one operation that just is slow. The fact that it tapers in kind of gives us a hint that like there are a lot of levels to this networking stack, and they all might be adding some amount of overhead. Because if you look at like the amount of time we spend in kind of the bottommost lowest level function, which goes all the way down to like the OpenSSL, OpenSSL C library, like reading and writing, the time it takes in there compared to the time it takes at our highest level read is quite a lot less. So there's some opportunities to dig further in here and see what we're spending time on, like in the middle of that stack. Another cool thing we get with these profiles is it's a nice way of comparing before and after. So here on the next slide, we have a view of the same workload running on the same cluster on the same infrastructure. The upper one is that workload, that shuffle workload running on version 2.30, which is from like late 2020. And the lowest one is the same workload running on main as of a couple days ago. So sweet, it's faster. A couple things to notice here are that like, if you look at the top one, that time on the left, the idle time on the left, where we're waiting for something from the client, is way longer than on the lower one because of all of this work on high-level graph serialization and sending high-level graphs to the scheduler. You can see that it takes a lot less time for the scheduler to have something to do. And maybe the cool part, next slide, is that the time that it used to take us to just send the low-level graph to the scheduler is more than it now takes us to send the high-level graph and to unpack it and to start computing. So like we've already, on an old version of Dask, like we can already start, or on a new version of Dask, we can already start computing your problem faster than it would have taken to even find out that there was work to do with versions of Dask. So this is really nice because one, great, we're doing better. Two, we're doing better in the way that we thought we would do better. So it's a nice confirmation that like all this effort around high level graphs has paid off and is having the effect that we would expect it to have. Now there's also something else going on here, which is like a little less obvious, which is that the actual compute part is a little faster too. if you chop off the like wait time, just the time spent computing, we do that a little bit better. You can even see it visually if you squint, where like all the like little slices of functions running in the compute section, they like look a little bit narrower and kind of tighter together in the lower one than in the upper one. And so next up, we're going to have John talking about some of the optimization efforts on the scheduler itself that have helped make this happen.
Thanks, Gabe. Yeah, so we're going to talk about Scythonization. As Gabe showed in the profiles, we noticed that transitions was somewhat slow. So we wanted to spend some time taking this code and moving it from Python into C. And in addition to that, the high-level graph work put more pressure on those transition functions. So it's even more important for them to go faster. So I'm going to just talk a little bit about how we approached Cython in the distributed code base and kind of some general patterns that we used. Next slide. Yeah, so this is taken from a common thing that you've probably seen before from Jake Vanderplas, where he takes a pairwise distance function and he implements it in something like pure Python and Numba and Cython. So we have the pure Python side over here where we could imagine we have some array that we take in. We get its shape along the first or the 0th and the first axis. And then we just iterate through in a nested for loop and accumulate all of these different results and store them back into that matrix. If we want to Cythonize this code, we'd go through and then we'd say, well, we want to do this. We want to eliminate any bounds checks around that for loop. We want to eliminate any wraparound checks. So these are these decorators at the top of that pairwise Cython function. The next thing that we'd want to do is we want to say that we're not just taking a generic object in, we're actually taking in an array and an array that's C-strited so that we can optimize handling of that array. And then after we do that, we would say that the shape has a particular type. It's actually an integer. Python calls this pi_size_t, but it's just generically a large int. So we type both of these variables. We type any temporary variables that we use to match the type in the array. So these are also double. We type the array that we're going to use for storing the result itself. And if you look at the code isn't too different. We can now also use square root from the C library instead of from NumPy, but more or less the code is the same. Next slide. Yeah, so this is great. So when we write code in Cython, we can get C-level speed. And if we're very careful with the typing and how we write the code, it can even be turned into the same C code that one might write by hand from scratch without Cython. It looks very similar to Python. So it's something that people are kind of familiar with. If you've written Cython before, you already know this. So it's easy-ish to maintain because of that. Cython does a lot of the nice things for you around like incrementing graphs and decrementing graphs and kind of adding all that interface code so you don't have to see too much of that or think too hard about that, while still keeping this dynamic flavor that we're all familiar with in Python. However, there are some things that aren't great about it. In particular, it's no longer Python. It's now another language. It's a little harder to debug because with Python, maybe I could just use PDB and kind of step through this code. Now with Cython, I'm having to compile this code. So I have to even get the compiler stack installed, which is sometimes a challenge for people and may be more or less of a challenge depending on the operating system you're on. And then this also adds another challenge around packaging. It's gotten a lot better these days with wheels and conda packages and all of this, but it's still a little extra work and something that's a little harder for people who aren't familiar with that stack to engage with. Next slide. So we can actually approach this in a different way. Cython has this support for type annotation. So if you're familiar with type annotation in pure Python, it's very similar for Cython. And so this lets us get at the same features that are good about Cython, namely being able to type the variables and get these low-level C types while still having something that looks Python enough and is runnable as Python. So if we look kind of generally at a function f that just takes an argument that's, let's say, a double, and then has a few integers that it works with, and maybe has a temporary variable. We can see on the left side, we would have said, you know, here's this double X, and here's these CDEFs for these different variable types. But on the right side now, what we say is, oh, just annotate X as a double and annotate A and B as these pi size t variables, and then annotate temp as a double. And so when we do this, since it's a type annotation, we can still actually run this as pure Python code. We won't get any optimizations when we do that, but the benefit is that we can still engage with people that are used to running normal Python code and want to add more Python code to this. However, if you're really interested in those speedups, we can then pass this same pure Python file to Cython. Cython will see these annotations and I'll go, oh, hey, I can actually replace this generic Python object with a C type. And oh, I can make this code more efficient now that I know that type. Next slide. Yeah, and so just to add on that a little bit, and this is actually pretty important for the scheduler too. And I don't know how much people know about this. Certainly you can always type things that have C types, but you can actually type built-in types for Python variables as well. So for example, if I know something's going to be a dict, I can annotate it as a dict. If I know it's going to be a list, I can annotate it as a list. Same thing for string or any other built-in type in Python. So why is this interesting? Python actually in its C API, it has special functions for these specific objects. So if it knows it's getting a dict, it can actually, instead of just calling a generic get item kind of function, it can call something that's very specific to dict itself. So this cuts out a bunch of overhead where you would have had to, at runtime, determine which object you're working with and then dispatch the corresponding thing. Instead, you pick an appropriate method that fits that type, and you can get some speed up from this as well. Next slide. Yeah, and so this is maybe somewhat similar to people that are familiar with Cython. So if you know Cython, you're familiar with typing functions as CDEF or CPDEF. But generally, what I'm trying to get at here is that when you're exposing functions to the C API, you can annotate them in different ways that have different benefits. So normal Python function, it's going to have higher call overhead because we kind of have to generically say, oh, this is some Python object, but I don't necessarily know it's a function. I have to kind of check and see if it's a function and try to call it. There's some kind of special things in newer Python versions where you can detect and have fast Python calls. So it may also check for this as well. But you have some general overhead for every Python function you call. And if we think back to the profiles that Gabe has shown, every Python function call, especially as they get deeply nested, has some overhead that keeps adding to that overall runtime overhead. So we want to cut that down as much as we can. The first thing that we can try is we can basically make that function a CDEF function, or in the pure Python mode, we decorate it with the cfunc decorator. So this is this middle line of sci-add. And so what this basically says is it says, oh, in Cython, just say this is a C API function call. So it would be the same as if I wrote this function C and said, it takes 2 doubles and it will return a double. And that's the interface. So it's very fast to call in C. There's no dynamic determination of what kind of function it might be or any kind of special exception handling around that function. So that keeps it very fast. If I want to use that same function, both in Python and in C, then I can use the C call, or in Cython, what you call CPDEF. And so what this says is add this very efficient C API. And if you can see that I'm actually calling this function, use that efficient C API, but also supply it like a Python wrapper around that C API so that users in Python can still call into that function. They have some overhead for making that call into that from that Python wrapper function instead of maybe just using the normal Python one at the top, but it's not a huge amount of overhead. So you have these options to kind of choose how you interface with these different functions. And the more that we use these latter two cases of cfunc or ccall, the faster we can get those calls on the C side. Next slide. Yeah, and so to kind of point out a few other things that you can do around the Cython functions, and you could do these things in Cython as well. You might choose to note that a function doesn't actually need the kill. And so then that's basically tells Cython, actually, this can be all written in straight C. And so you can keep this code very efficient. And this cuts out a lot of boilerplate. you can say that this function can be inlined. And so then Cython doesn't necessarily inline itself, but it tells the C compiler this function is inlineable. So you may want to consider trying to inline it in some cases. So for something as simple as this like add function, which of course is just trivial for this example, but if you have a similarly short or simple function and you can note that it's inlineable, then the C compiler could say, oh, hey, yeah, actually strip out all of the C function call and just stick this code straight where I need it, and then do any additional optimizations once it's in place. Next slide. And so this last point is that inside of the scheduler, there are multiple different objects. There's objects that represent the task and its state while it's running on a worker, where it might be running and all of these different things. It may also have information about different tasks that are grouped together or similar in different ways or related in some fashion. It also has information about the states of the workers that it's interacting with, and the scheduler itself has its own state. So all these objects in Python, they're going to have a lot of overhead to interact with. And so if we want to make sure that they're working very efficiently on the C side, we really want to take advantage of Cython extension types or Cython classes, as you may be familiar with them. So this is the CDEF class in Cython, but here it's the C class decorator that you see at the top. And so when we apply this decorator to a class, then Cython says, oh, hey, I can actually optimize this class a little bit. In particular, the optimizations that it will do is if I annotate attributes, say like here we have this point class, I have X and Y as attributes on this class, Cython can say, oh, let's actually stick this in a C struct. And so when it sticks it in that C struct, you have the speed of accessing any field inside of a C struct. So it's much faster than doing some attribute access on a Python object where you're having to do all of these checks of does it exist and error handling and this sort of thing. It can just straight put that right into any function call that you're using that particular attribute in. And so then we can have constructor, which we've annotated here. And one kind of point that's worth mentioning about attributes specifically, if I just add an attribute like I've done here with X, this is only going to actually be visible in Cython when it's compiled. And so this is actually kind of an important point. If I do want to access that attribute, I need, in Python in particular, I need to add these properties that you see with Y down below. So if I add the normal just add property, then I can access this in Python as well, or I can add a setter function to also allow me to override the value. In Cython, I can, of course, just access these attributes directly and override them, but this provides me a way of accessing them in Python. And one last thing that's worth mentioning here, with Cython classes, you can inherit from them, and there's some additional overhead depending on which way you inherit from it. So if I inherit from another Cython class, what will happen, for those of you that are familiar with C++, you get what's called a virtual table of methods. So if I'm overriding any method in any of those subclasses, I may not know which method I'm calling. So I keep track of pointers to whichever method would have been called. So for Cython classes that get inherited from, you have this first layer of overhead. And then in Python, you have an additional layer of overhead associated with generally checking if something might be a function and trying to call it in Python, or checking to see if there's this virtual table, if it's a C related thing, or if it's never overridden, maybe you can call it directly. But if I know that this class will never be overridden by anything else, I can declare it final. And this is actually very powerful because what this says is it says actually all of these methods can be turned straight into functions that just take this object as the first argument. And so that's very nice because those functions have all the same properties of any normal function. They can be inlined and you can do whatever kind of cool things that you want with that. And you look at the C code and it's literally like I've defined a struct and I've defined several functions that take that struct and do different things to it. Yeah, and so next slide. So James is going to take over with concluding thoughts.
All right, I guess I am. Next slide. Thanks, John. Yeah, so some key takeaways. First and foremost, profiling is hard, as Gabe and John have both discussed. Also, we learned that high-level graphs are one honking great idea. So both Rick and Mads went into a lot of detail about how expanding and extending high-level graphs throughout Dask really helped us improve our performance, in particular with that initial sending your graphs from the scheduler to, or from the client to the scheduler. And because of that, we see today task submission is fast, generally speaking. You can optionally disable low-level task fusion for any Dask object, and it will be sent, a high-level graph will be sent to the scheduler from the client. Today, that's actually the default behavior as of the latest Dask release, which I think is 2021.5.0. That's actually the default for data frames. So if you're doing data frame things, task submission will be much faster by default. However, we're still searching for that 10x performance improvement or something roughly of that scale. So those are some key takeaways. Next slide. We do have some ideas for future work, and we would also love to have a lively discussion in Q&A session after this to discuss some of these proposals. So we have speculative task submission. This is where the scheduler can start assigning work that's not quite ready to workers, and have the workers have the task already be submitted for the worker to pick up when it becomes ready to execute the task. Async disk spilling, more Scythionization, as John has discussed at length. Investigating garbage collection pauses. This was an interesting result from Gabe's recent profiling using PySpy. We see these strange gaps that coincide potentially with garbage collection happening on the schedule. There's also overhead associated with Tornado. We might look into switching to async IO directly instead of using Tornado. And also continuing to optimize our scheduler transitions with C calls. And with that, next slide. High performance computing isn't about doing one thing well. It's about doing nothing poorly. So with that, I want to thank everyone who attended this session, and thanks for the time and your attention, and maybe open it up to Q&A discussion, or maybe bring Ben back in as well.
Yeah, it looks like we already have a couple interesting questions in the chat from earlier that we could talk about. I think those kind of lead into good things to discuss.
Discussion in the Slack channel already. So if people haven't already joined, if you're on the Dask Slack, there's a workshop doing nothing poorly, accelerating Dask scheduling, all hyphenated. You can join.
I'll just quickly answer. Tim asked about this is the default for data frames. What about arrays? Arrays coming soon, not yet. There's arrays are a bit more complicated. And so Rick has done like the core really important work to enable this. And now we kind of have to go through and like apply his work to a bunch of different places in arrays before we can actually turn on just use high-level graphs for everything in arrays. And there's also some more optimizations we have to figure out. So arrays are a little further off.
Cool, thanks. Looking forward to it.
I can maybe share my screen for a second, even like zooming in on what Gabe just said. Here's the default optimization for arrays. And so you'll notice there's this config setting down here, optimization fuse active. This is basically the quick fail, or the quick path where all the optimizations happening above here are all high-level graph based, and all the optimizations down here, we convert this thing to our task graph to a low-level graph here. So you'll notice there are a few optimizations that are still happening down here, which have not been elevated to high-level graph optimizations yet. In particular, this last one, optimize slices. So we're currently working on moving some of these optimizations above this portion where they are high-level graph aware.
Thanks. Cool.
Davis has a question.
Yeah, this isn't necessarily about the performance of the scheduler per se, but more about, I guess, like cluster health. Is there any mechanism for responding to workers, basically getting feedback from workers about out of memory issues? I often run into issues where something that works with a small number of workers, or something that works with a large number of workers will fail with a smaller number. And I think it's essentially because I'm giving workers data or workers are generating data faster than they can write it to disk. And there's no mechanism to back propagate the that information. So this is probably a separate target from the optimizations you're talking about, but it's still an issue.
I think for you can go, James. I think for to me it sounds like it could be memory, or there could be other problems there. I'd want to dig into. But
there's an ongoing effort for there's like a long memory back pressure.
Yeah,
issue,
that's the issue basically that I would.
Yeah. This is still an active area of improvement, and yeah, that's I guess I'll leave it at that. Thank you, Ian, for linking to the issue in the chat.
There's a few from Gail on how many processes, threads, cores run the scheduler. The scheduler is single threaded, single core. Can it be parallelized?
This is a question that we're asking ourselves. It's probably complicated, as with most good questions, because you are operating on this graph that does have all of this interlinkage going on. We have to very carefully explore that, since this would also probably involve some releasing of the guild. That's something that we still need to explore. But the more that we've Cythonized the code and pushed it down into kind of the C layer, the easier that will be to do. Yeah, I hope that answers the question. Maybe as a first pass, we're more focused on seeing where the guild can be released for long periods of time. For example, right now, we're using Tornado for doing communication. When you do any socket sends, for example, you just release the guild around that. We're looking at UV loop as a library that we might use for communication. We use it for some of the async operations, but UV loop can release the guild for long periods of time because it uses libuv to do a lot of this event handling and communication stuff on the back end. So maybe the short answer is, first, let's see how much we can get rid of the guild. And then from there, we can start to investigate other things like threads.
I'll maybe jump in briefly. So in Dask world, like we often look to parallelization as a solution for performance. We think, oh, like this is slow. How do I parallelize it? Parallelize it means fast. Like the scheduling logic is like extremely complicated. It's not like a data parallel operation. There's a really complex state machine that you want to just like churn through events as quickly as possible in a very sequential way. It's very much a sequential problem, right? It's not a parallel problem intrinsically. Problems like this are often don't benefit from parallelism. If you sort of try to like, historically look at problems like this, you try to put locks on different kinds of state, and you try to sort of like have some weird message queuing system that handles these events between those state. And you're usually lucky if you spend a year and you're only 5 times slower. Like these problems are notoriously hard to do well. It's not a parallelizable problem, probably.
I think that addresses the second. Sorry, somebody wanted to also address that.
Oh, I was just going to kind of reiterate what I said in Slack, which is sort of building off what Matt said. Like, it's not a easy problem to parallelize. It's also potentially not the right approach to parallelizing it isn't necessarily the thing to do. Like, computers are super fast, like if you can get the computer to be doing just the right things, like it could theoretically process like transitions ridiculously quickly. And so I think we're kind of interested in looking at all the reasons why why the computer isn't as fast as it could be.
Mhm.
Like if you look at, very high performant, like even look at like Postgres or something, like it's kind of crazy the performance you can get out of a like very well tuned system that uses hardware well. You can get really good throughput. So I think we're kind of interested in like in that approach, and like we saw in the profiles, like we spend a lot of time in transitions. We spend a lot of time in other things than transitions too. And so I think we're interested in like what's the overhead as opposed to like how can we make the very core thing parallel.
Yeah, to build on that a little bit. So like speculative task assignment is a little bit trying to move some of this work onto workers. Like workers are already there as something that can parallelize work. So then you're not thinking about threads on the scheduler necessarily. You're just thinking about workers being more engaged in that process of what gets run when. And so there might be some simpler answers that are along those lines.
So Gal
Simpler.
responds saying, so Gal doesn't have a mic, so he's responding in text. I'll speak for him briefly. And he says, there's examples like maybe building of the graph could be parallelized. So we have all these different layers in the graph, and maybe that is something that could be parallelizable. And that's a great idea. That's a segment in the pipeline where I think there are opportunities for parallelism. And everything is, Gale-free because of the work that Sean is doing around Siphonization. Then yes, that sounds like a great opportunity. The last question Gail posed was, have you seen Dask on Ray? Is there inspiration to get there? I'll maybe briefly answer that. So Dask on Ray is solving like a different class of problems. Like it's solving much more like easy to parallelize set of problems. If you look at like the entire pipeline we're doing, stuff like the client work, that's going to be there regardless of what Dask scheduler you use. The serialization work is going to be there regardless of what scheduler you use. Like just is again kind of the same as before. Just throwing parallel scheduling at the problem isn't actually likely to solve 80% of the problem. You kind of need to solve the entire pipeline. If you look at operations like the shuffle operation that we're using as a benchmark, I think Dask on Ray actually historically performed notoriously bad on that benchmark. They had to reinvent their own shuffling algorithm because their scheduler couldn't perform on it well. So again, it's one of those cases where sort of just throwing parallelism at the problem may not be appropriate. It may be that we can get from 5,000 tasks where we were a few months ago to 100,000 tasks just by thinking a bit more cleverly about what it is that we're working on, sort of doing a holistic optimization.
We have another question from Andrew. Data frames are an example of a hinted data type. Is there an effort to identify other data-driven patterns that could help the scheduling problem? I take that question to mean, I think that we are engaged with a lot of Xarray folks who also have very large scheduling problems. If you read from lots of ZAR files, if you're doing lots of complicated array interactions, then you will also run into these. It's not just a data frame problem. That's the question that you're asking.
It might be worth mentioning that at this level of the scheduler, Dask has no idea if you're running a data frame computation or not. We're lower level than that at this point.
What resource is the dashboard sharing with the rest of the system? Main process, scheduler, workers? I think Gabe, you maybe answered this earlier.
Yeah, I mentioned this in Slack. Currently, the server side of the dashboard, because it is, a fair amount of work is done in your web browser as well. But the server side that's like pushing all the updates runs on, it's in the same process. And it's all async in theory. Well, it is async, but there is some overhead from the dashboard in some cases. And I think that deserves some more attention in the future.
There's a question from Bruce Mary. How important is network bandwidth? Does a fast network help, or is the serialization deserialization CPU bound? Mads, do you feel comfortable answering that one? I can repeat the question if you prefer.
Yeah, could you do? What was it?
Yeah. All right. So question from Bruce is, how important is network bandwidth? Does a fast network help, or is the serialization and deserialization dominant?
Yeah, so of course, at some point, a fast network will help, but it's true that serialization takes up a lot of the overhead right now. And what we're doing right now is many passes when serializing. So we basically go through in Python, go through the messages we are sending and receiving many times and taking stuff out. And I'm trying to explore an approach where we can do this in one step. The thing is, if you're using MessagePack, it's actually implemented in Python, so it's very fast. But all these passes we do manually in Python in Dask, just both before and after serialization. Those are in Python. So if you can kind of fit everything into MessagePack or in other library, look into some MessageSpec and some other serialization libraries that also are safe, then that I think that could be a significant speed up. Yeah.
Perhaps Gabe can also maybe jump in. I know,
Yeah.
I know living in New Mexico, he's had some experience with reduced network connectivity.
Yeah, I actually have
There's a
this
slide for this, I think, actually. Yeah.
have this slide, which hopefully you can all see right now. We left this out of the original the presentation, but this is some more of my profiles, where the uppermost one here, this is all the same workload. Again, this is that workload run from my laptop in New Mexico, connecting to AWS data center in Oregon, which is like 1,600 kilometers. And then we drop down and we see the exact same workload with the same version run from where the client is also in the same AWS data center. And you can see like very, remember this part on the left is the like sending the graph to the scheduler part, like very big difference between driving the computation from, New Mexico to Oregon versus from like Oregon to Oregon. And I think the cool thing here is that now these lower two ones are this same scenario, both cases of this same scenario run with the most recent version of distributed. And the difference between driving from my laptop and driving from the data center is much smaller. Like it's pretty cool that just by upgrading the version of distributed now, now the entire computation completes faster than it took the computation to even get to the scheduler originally. The reason this joke came is like, my internet is not very good in New Mexico. And so like, I'm a good test case for poor bandwidth. But a lot of people are gonna have scenarios like this. So if, maybe this is somewhat unrealistic, but like, if you realistically live in a place where the internet's not good, this is very relevant to you.
Absolutely.
I think that's a good example. It's very common where it's not like if you're on a Slurm cluster or you're in HPC world where you might do something on an edge node, but you have very powerful compute nodes, you might not have the ability to generate your graph quickly, and being able to push that off to the scheduler, which is hopefully running in the compute area, you'll be able to take advantage of this. We also heard a bunch of talks today, probably yesterday as well, about people doing heterogeneous computing where they have very large nodes and very small nodes. You will want to do these kinds of things where if you're submitting from your client, if that's running in AWS or somewhere else, you are not going to be able to generate that graph as quickly as you otherwise could. That should be on a very large beefy machine.
This is also important for us at Coiled, if you don't mind me putting on my for-profit hat for a second, because we wanted to get people out of having to run on some attached Jupyter notebook to their Dask cluster. We want to get people today so they could run Dask from wherever. And the large task graphs are this big heavy thing that you need to start moving between those 2 points. And so for accessibility, if you want sort of anybody to run Dask anywhere in their own infrastructure, this ends up being really important. That distance ends up being really, really key, especially as the graphs get larger. You get million node graphs that you want some student in the Philippines to access some massive data set that's stored in Europe. like you sort of start really caring about the abstract formulation that the high level graphs provide. Are there other questions?
Was an older question that I think we missed. I just found in the chat. Said, what resources is the dashboard sharing with the rest of the system, main process, scheduler, workers?
I think Gabe answered the question a little while ago, and the answer is that the dashboard is co-located with the scheduler. It's in the same process. This is inefficient because it does claim resources from a highly critical code path, but it also allows the dashboard to access all pieces of data in the cluster, which is actually really, really key to how Dask gets the beautiful dashboard that it has, to have very close access to everything there. So, but that is something that one could imagine pulling out in the future. In principle, like when people are running very, very large workloads, we just don't use the dashboard. Or we'll try to make dashboard plots that are less performance hungry when running at scale. And there's some effort in that.
And I think this also gets back at these questions about parallelism. I think people are asking about parallelism of graph, but the scheduler itself is engaged in multiple different activities that aren't necessarily related to each other. And so maybe just making those more efficient and less interactive between each other or blocking of each other may just help as well.
Yeah, that's an interesting point. But I mean, at the same time, like the fact that the scheduler is inside the exact same event loop as the dashboard means that the dashboard code gets to do really complicated stuff on the scheduler state and know that it's always safe to do so. And the alternative is to start putting locks everywhere and to start really like defending your access of that state. And that's where things end up getting usually a lot slower. I would be much, much more excited about how this community can design dashboard plots that scale better. So how, sending something to a dashboard server should be 1% of our CPU load if we can start thinking of better plots that are easier to generate.
A new question, what part would you recommend a new contributor interested in this project look at, if at all? Do you mean the scheduler or Dask as a whole? Assume you mean the scheduler.
Dror, you should also feel comfortable jumping on and speaking if you're okay with it.
Mute.
Yeah, he's specifying, particularly on the performance stuff.
In that case, do not unmute.
Yeah, so are there things that this group is doing around optimizing the whole pipeline of a Dask computation that could benefit from someone who's coming into this group new and fresh? Is there testing, for example, or are there particular parts of the computation, maybe high-level graphs, that could be parallelized out?
Yeah, I can't say that for a high-level graph component, especially like taking advantage of blockwise IO so that we can move things over to array. I know there are already people thinking deeply about it, but in the long run, I think that there probably are parallel efforts that could happen at picking off the necessary things. So yeah, we should probably raise a discussion about this somewhere on GitHub and start talking about this in more detail. But
maybe to augment what Rick is saying, we've written all this Dask code and it's all in sort of low-level graph form. And now we're going through that code and we're sort of up-leveling it, so it's slightly more abstract. And so that is a lot of, I don't want to say tedious because it's actually really complicated, but a lot of work that can be spread around, I think. And we've seen other groups sort of see the benefits of high-level graphs, want that to happen for themselves, and then start working on that themselves. So like the imaging community is starting to do this inside of Dask Array.
But just another quick point about the high-level graph stuff is that, just the other day, maybe it was 2 days ago, somebody did raise an issue because we switched the default and it looks like there's something about serialization and blockwise. It doesn't quite work. We're passing in futures in a certain way. So there are things like that, which, things are breaking in data frame. And so if we can preemptively test things with active fusion turned off in array, that will make things happen faster, I think, as well. So just want to put that out there.
Valuable.
John, is there any siphonization work that can be parallelized?
Yeah, maybe. I think the we haven't really Pythonized the update graph and update high level graph functions that much. They've been done lightly. That might be a good place for somebody to start. Mostly just adding types where there aren't types. That would be a good starting point. There's still a little bit of communication that happens in there. We've generally kind of moved that as far out as we can, but that's one of the places that it hasn't happened. That might be something that somebody could contribute to. I think I have like a WIP PR, but somebody could build off of that. And I don't think it'd be too hard.
I think looking at the dashboard too, it sounds specifically for you, like it sounds like I know Matt often recommends people to look at the dashboard because it's a useful and a good way to kind of learn about how things work. But it's not something, the performance of the dashboard is not something that we've looked at as carefully, just sort of like seen it side-eyed in profiles and been like, oh, we need to go deal with that sometime. And I think someone digging deeper into the performance implications of dashboard and like seeing if there are any ways to optimize some of the logic that generates those plots would be really, really beneficial to lots of people. It is not something that we have focused that much effort on yet.
I think with regards to the dashboard, there's a point that you brought up, Gabe, when we met, I think last week. With all these white spaces that are in the Dask dashboard, it'd be really great if we could hook into other tooling to inform what's in those white spaces. Maybe optionally, I don't know how you'd go about doing that, but if you had a time series of what else was happening there that the Dask profiler wasn't able to pick up, that would be immensely useful.
Yeah, what the workers are doing when they're not working.
Yeah.
I don't know if this is the best issue, but there was, I think, an issue Matt raised about making the task stream more efficient for large computations. I think there might be some other issues I'm not thinking of that are related to this, but this might be a good place to kind of share some ideas or what you're looking for.
Martin Durant, also Martin, feel free to jump in and speak if you care to speak, but I'll speak for you unless you jump in while I'm saying the sentence. Martin says,
I'm here. Sorry, I was just
fantastic.
Yeah, I was just for information for anybody that does want to help. I would suspect that the different panels in the dashboard do end up repeating some work and producing the things they produce. Do you suppose that's true? Whoever wants to take ownership.
I think they're fairly well isolated. I mean, they do have some patterns that are definitely repeated where like they have access to the scheduler and like they're like looping over task groups or something like that. Like that iteration may be something that happens in different dashboard plots, but I don't know that there's a ton of reusable code between the different dashboard plots, if that's what you're asking about, Martin.
Not reusable code, but yeah, walking the same data structures repeatedly for different views.
Yeah, just to kind of add to what you're saying. I remember going through the stealing code because that was kind of slow at one point. And so it was fairly easy to just move one piece into a method that lived in the scheduler and got Pythonized, which sped it up quite a bit. If there are iterations like that that people are finding slow on the dashboard, it may make sense to do similar things. I don't know if other people in this group have thoughts on that idea.
We have a few minutes left. What I would suggest is if someone wouldn't mind resharing the slides again. Gabe had a great slide which broke down the current like distribution of costs. I'm not sure if this was Pythonized or not Pythonized, but you're muted, Gabe, by the way. Thank you, James, for owning sharing.
Sorry, where is the slide?
One up, two up from that, I think.
Yeah. So I mean, this shows maybe where we should be focusing our efforts over the next few months. And people are talking about things like the dashboard, they're talking about, parallelizing stuff. Like this is, I think, really what we should be like focusing our conversation around this stuff, right? So like on the right, there's Tornado. Like someone should be looking at, what does it look like to replace Tornado with Async IO or with some other experiment? I know Jim Christ has like a half dozen experiments around fast networking. Like maybe there's something there we can try. There's high-level graphs. Like what does it make sense to Cythonize there or just accelerate there, right? And that's another sort of interesting question for us to think about. There's reads and writes. I know that's maybe rolling into some of the serialization work, but that's maybe another chunk. And then there's the actual like scheduling transition stuff, which turns out to not be, like we've kind of whittled that down fairly far. And so like the things to actually think about, things to focus our conversation on should be sort of informed by, I think, this page, if that is, we believe this page. And as we all know, all the profilers are wrong in different ways.
If indeed the dashboard was running.
Sure, yeah, when the dashboard isn't even here, like we're not seeing bokeh.
It was actually really particular to not look at dashboards during any of these profiles, just to make it consistent, which was frustrating at times because I was like, what's going on? But I had to hold myself back and not open it.
But I would encourage people to think about questions or thoughts around these topics, because these are the topics that appear to be important.
I think it's maybe also, I'd be curious while we have a couple minutes and everyone is here in one place. I'm kind of curious how much this speaks to people in the audience as like, yeah, the scheduler performance, or like white space in the graph, or like the schedule performance is a bottleneck for me in what I'm trying to do. We've had there's been some discussions throughout the summit about like memory management and other things. And these are all kind of interrelated, but I think maybe another thing that we were talking about is like, is this the place to focus efforts, or there are perhaps unexpected ways that improving things in other places can actually improve what this profile ends up looking like?
We certainly do at the moment push people to larger tasks at the risk of running out of memory, because this used to be a problem, and probably we could at least update our recommendations on what makes a reasonable sized task.
Yeah, there was a great talk in the Pangeo workshop earlier yesterday, where I think Deepak was showing how like memory stuff was bad. And so he just rewrote some Xarray commands to use like different kinds of graphs. And as a result, like actually Xarray ran beautifully. And so that was something where I think a downstream project was able to change how they operated. And then they could have far fewer tasks, have far larger tasks, have much smoother memory performance. Now, clearly, I think it's our job to assume they're not going to do that, to make things fast regardless. But it is interesting seeing how different subcommunities can solve their own problems by thinking about making better algorithms.